we have to go back to the other page.
Okay, I'll go back. So, forgot to record for the
Gotcha.
posterity. There's first page, factor theorem, right? All it's saying, if f of k is 0, then that means that x minus k is a factor. That's no big deal. And I will be sure, today, like at lunch, I will put this stuff on my notes on Algebra 2, because this is one you want to refer to. So I will put it up. So if you go to, you guys know how to get to the notes, right?
Yep.
Algebra 2 page, top block is instructional videos and notes. Go to the notes link, and this will be the most recent one, right? Okay. So, back to this. Determine whether this binomial factor is a factor of f of x, okay? If it is, then we're gonna factor it. We're gonna factor the whole polynomial, right? Write it in factored form, completely factor f of x. If it's not, enter n, but none of them are n, I don't think, can't remember. But that's not the point. The point is not to, the point is I want you to practice factoring these things, right? So how are we gonna do this? What do you think? How could I check to see if this is a factor of f of x? That's the factor theorem. What do you mean plug it in?
I was gonna say synthetically divide.
Sure. Right, synthetically divide. So the remainder, right, the remainder should be 0. If this is a factor, then when I evaluate the function at the 0 of that factor, I need to get back 0, right? For the value of the function, which is what shows up in the remainder box of synthetic division. So, if we just set this up then,
You should have just added a yes or no.
no. That's nice and weak. So what do we get then? What are my coefficients?
10, negative 23, 2,
And what goes out front?
2.
Good, the 0 of the factor, right? And what do we know, if it is a factor, what has to happen?
Zero.
We gotta get 0. Good. Okay, so what do we get? If we do synthetic division on this, 10,
Oh, yeah.
so then, right? 0. So it is a factor. Yes, it is. Okay. How does that help us?
That means it's true. So it's a function x means that 2 is a.
So 2 is a factor, but how are we going to keep going? We want to factor the whole thing. What do we do?
You just divide it out with x minus 2, so you can just write the x minus 2 is minus that.
Okay, good. So what this tells us, that what this synthetic division problem tells us here, is that this, right, so there's our polynomial, 10x cubed minus 23x squared plus 2x plus 8 divided by that, x minus 2 equals that, right? Which is, so that must be my constant, coefficient of x squared, right? So that's like, there's an x there, oops, sorry, there's nothing there. There's an x there, and an x squared there, right? So it's all equal to 10x squared minus 3x minus 4. So, in other words, we don't have to write this all out. We could just jump down to the next step. If I were to multiply each side by x minus 2, right, I'm just getting 10x cubed minus 23x squared plus 2x plus 8 equals x minus 2 times that. Right? So that's what, so far that's what we've done. And did we have to write all that out? No. No, but the synthetic division was important, right? We knew that when we checked this factor, or this zero, same thing, it was, that is, 2 is a 0, so x minus 2 is a factor. That's the other factor that it's being multiplied by, right? So we can immediately, from the synthetic template that we developed here, we could just jump down to there, right, to that row. And so we're in the process of factoring. Now we just got to see if we can factor that quadratic. Okay? And so, yeah, what are our options here, right? So we're down to
It doesn't matter. That's 10.
Oh, that's.
okay. So now what are our options? We got to try to factor that thing. We could. Really we got two, don't we? We could do bottoms up, right? We could try bottoms up, or we could use the quadratic formula and cheat using the quadratic formula. If you kind of reverse engineer the quadratic formula. Let's just look, not because I'm so anxious to I love this problem so much I want to do it a bunch of times, but to illustrate those relationships this one time, let's just do both of those.
Do them all.
So method one, what if we just apply bottoms up? Okay, so we know for bottoms up, we've got a 10 and a negative 4, A and C. So A times C is what?
Negative 40.
B is negative 3. So can you think of numbers that multiply to negative 40 and add to negative 3? Negative 85, right? Good. And so bottoms up, then we're going to split this thing up. This one's going to split up into x, you said negative 8, right? X minus 8, x plus 5. But I've got to divide each one by a, right? And then I just simplify the fractions and go bottoms up. So 8/10 reduces to 4/5. Five halves reduces to 1/2, and so what do we end up getting out of this stuff?
5 minus 4.
And 2x plus 1.
And that's
Okay, so there's our answer, right? Using bottoms up. Okay. So what if bottoms up is hard, or it doesn't work, right? Bottoms up really only is going to work for us if we end up getting rational zeros, right? Think what rational numbers can be written as a fraction, so fractional zeros. What if we got square roots in there or something? Bottoms up is hopeless. It's not going to do us any good.
quadratic formula.
But quadratic formula, we can always cheat with the quadratic formula, right? So if we were to, we're just gonna use the thinking that we've already invoked today. We're gonna think about the factor theorem, and we're just gonna utilize the factor theorem to find the zeros of this factor and convert those into factors, right? So by the quadratic formula, if we set this thing equal to 0, so then by the quadratic formula, what's x equal?
Negative 3, positive 3.
So negative b, so I'm going to get 3 plus or minus square root of 169 we get, right? Okay, so I heard this. So and we get that from negative 3 squared is 9 minus 4 times 4 is 6. 4 times negative 4 is negative 16 times 10 is negative 160, but I'm subtracting a negative, so I'm adding it, right? You got to be careful about that. I've seen people make that mistake a few times. When you're applying the quadratic formula, if we're always assuming a is positive. We would always make a positive. If we set a quadratic equation equal to 0, we always want a to be positive, right? That just makes things, it normalizes things. It's Not gonna change any answers, it makes the algebra easier. So A is always positive. If C is negative, that always means that the sign inside the radical in the discriminant is gonna be positive. That does, the operation is adding instead of subtracting. And so that's all divided by 2A, so that's a 20. Well, the square root of 169 is what? 13. So we get x equals 3 plus or minus 13 over 20. If we take the plus, we get x equals 16 over 20. What's that reduced to?
Oh my goodness.
If we take the minus, we get negative 10 over 20. Okay, what do you know? Those look pretty familiar, right? We got, there's our 1/2, there's our negative 4/5, right? And so from that point, everything's the same as it was up there. Right now, we're just gonna have it. These are our zeros. Then the factors that must go with that would be x minus 4/5 and x minus negative 1/2. And then we wouldn't want to leave those as fractional zeros. We'd rather just, multiply each side by 5 and multiply each side by 2, right? Because this whole equation, remember, is equal to 0 for finding zeros, right? So multiplying 0 by anything just gives us 0. So I would multiply each side by, you clear the fractions, right? Multiply each side by 5, multiply each side by 2, and what would we get? So we get, what happened there? Oh, not sure. There's the glitch again.
That's what you're so excited to teach.
I'm excited to teach it all, but this is like real stuff now, right? So there's our factor form. We write it in simplest form, right? Okay? All right? How about that one? Now it says find all the real zeros this time, right? We're only looking for real zeros.
On one.
Okay, so we got one. One of them is negative 8. And it wants us to enter all of the real zeros, including the given zero. Right, so if we're keeping a list up here of all of our zeros. So one of them is negative 8. Let's keep going from there, right? So how do we find the others? Synthetically divide. Yeah. Coefficients?
0.
Ah, good. What do I know?
There's a 0.
Okay. We know that's true because it told us that it's a 0, right? Okay, what do we get if we do that math?
So f of negative 8 equaling 0 is the same as x plus 8
Being a factor.
being a factor.
Exactly. Yep. So now, real quick then, this is a different kind of problem, right? We're not looking for factors, we're looking for zeros. But it's 6 and 1/2 dozen the other, right? Same thing. Given zeros, we can always turn those into factors and vice versa. So what do we get here then? 64. What do you know? Negative 512. So we get 0, 0, 0, 0, 0, 27. And I bet that's negative 216. What do you think?
That's a good bet.
Okay.
Put my life on it.
And so then we know that we're trying to now, we got to find the zeros of this reduced polynomial. We already found one of the zeros. Now the remainder of the zeros that we have yet to find will be the zeros of this polynomial, right? Which is the other factor. Think of it in terms of factors. We would know that our original polynomial would break up into x plus 8, right, times that. Well, what is that? That's our constant, right? So there's coefficient of x squared, coefficient of x cubed. So 64 x cubed plus 27. Right, we want to find the zeros of that. Well, how are we going to do that one? This is good practice.
Sum of
Sum of cubes, right? That's got to be. And how do you know sum of cubes? Well, you don't. I mean, in reality, when you're doing a problem like this, that's just out of the blue. That's like some problem where you're faced with doing a larger math problem. You're faced with trying to solve this. Do you know it's always going to work? No, but that's the only thing you can try, really, right? Is you want to see if you can build this into a sum of cubes. Sum of cubes makes sense because I've got an x cubed and no x, right? So that's the only pattern that really would fit this at all, would be a sum of cubes. So can we write this as something cubed plus something cubed? Well, 27 is what cubed? 3. 64x cubed is 4x cubed, and so yeah, this does factor using our pattern. So I get 4x plus 3 times what? So it's going to be a squared, so 4x quantity squared would be 16x squared
Minus 12.
minus, good, ab, 12x plus. Okay, so we get another factor out of this, don't we? Another 0. So we get the 0. If I set this one equal to 0, what's the result?
-3/4.
So I can add that to my list. What was it again, -3/4?
Yeah.
Now we're looking for real zeros. Do I have to go any further? How come?
Because that's always gonna be I.
Okay, this is always going to give me, right, if I'm using any of the cube patterns, sum or difference of cubes, I get this irreducible quadratic that will never give me any real zeros. It's always going to give me a complex conjugate pair. So I don't have to go any further. Now, if this problem were different, and you're going to get some of both in the assignment, if the problem had said find all complex zeros, then yeah, I'd have to go use the quadratic formula and find both of the complex zeros that went with that, right? Okay, make sense? But for this problem, that's it. Okay? All right. Questions?
What is the sum of cubes equation again?
Sum of cubes. Okay, so real quick, what are the, let's just,
Yeah.
what are those patterns? So a cubed plus b cubed is what?
A plus B plus B. A squared minus B plus B squared.
Okay. Difference of cubes?
A
minus
A squared
plus
AB
plus
plus B squared.
There you go. Okay? Yes, sir.
Do you even need to do the sum of cubes on that? Or can you just, like, cube rooted?
Okay, it's a good question, and the answer is if you're only looking for real zeros, you can just isolate the variable. And we'll talk about that, that's coming up probably in about a month. About a month, we'll talk more, we'll kind of get into that part. Yeah.
We don't have much.
Go back to that last week.
I know, but we'll get through that. That's really all we gotta get through. Yep.
Go back to last week.
We haven't got that
To
one.
that one?
Yeah.
Okay, so next problem, refocus here. You can't train can't go off the tracks because you gotta stay focused here. They're getting more challenging.
You have exceeded our duration of focus.
No, not true. So what about this? Now we're looking for complex zeros.
Okay.
Okay, look what it gave you. So it gave you one complex zero. So this one, can I use synthetic division? No, I can't. Synthetic division doesn't work with complex numbers that have imaginary parts. Right? It only works for real numbers.
You take out squared.
Okay, so there's an important relationship here that you got to remember, first of all. What is it? If negative 4i is a 0, then I gave you a 2-for-1 deal. 4i.
Plus.
4i is a 0. Okay, and that comes from that relationship, right? It comes from the complex conjugate root theorem, right? Which it just says that if a plus I is an imaginary root, or same thing as a 0, right? An imaginary 0 of a polynomial equation with real number coefficients, then a minus bi is also a root. Okay, well, you know, we know that for it to be a polynomial, it has to have real number coefficients, right? For it to be you know, the way that we're defining, now you can, future math classes, you can, you know, when you do complex analysis, you can redefine a different category of polynomials that don't have real number coefficients, but that's for the distant future, right? A traditional polynomial, when we say polynomial in math, we mean that it has real number coefficients. And so if that's the case, you know that the zeros always come in complex conjugate pairs. So if you're given 1/2 of a complex conjugate pair, you can always, you know, take it to the bank that there's going to be another one that goes with that, that it's its neighbor, right? Complex conjugate neighbor. So if we write negative 4i as a complex number in standard form, what is that? With a real part and an imaginary part.
0 minus 4.
It's 0 minus 4i, right? So we get one root is 0 minus 4i. Well, what's the complex conjugate of 0 minus 4i? 0 plus 4i, right? Because complex conjugates are always in the form a plus or minus bi, right? So we get 0 minus 4i and 0 plus 4i. Well, we don't write 0. We'll just write that as a 4i, right? So there's two of them. How many total complex zeros does this polynomial have? 4. Okay, so if we know 2, then there should be how many more? 2. Well, that makes a quadratic equation, right? A quadratic factor, and so no matter what, once we get it down to quadratic form, quadratic formula is all we need, if that. Sometimes we don't even need that, right? So what do you think then? How could we approach this? Okay, good. So we could turn those into factors, right? So we know that our polynomial, x to the 4th plus 15 x squared minus 16 must equal x minus negative 4i, so that's x plus 4i times x minus 4i times some other factor, which I'm just going to call q of x, because it's got to be quadratic. Yes?
Can you multiply the two x1?
We can, and we'd want to.
Divide it.
Right, we want to. We want to multiply the complex conjugates because that's the only way we're going to be able to divide this thing out, right? We can't do polynomial division with imaginary numbers in there, right, as coefficients. It doesn't work. We've got to turn those into real numbers, but we can't, because if we multiply out complex conjugates, what's always going to happen, let's explore that for a second. If I take complex conjugates, just do this totally generally. If I do a plus bi times a minus bi, this is the product of complex conjugate pair. What am I going to get if I expand this out?
Squared plus b squared.
Yeah, right. We know this is our conjugate pattern where I'm going to get the first term squared minus the second term squared. Right, we already have this pattern. Without i's in it, this pattern we talked about a while ago. Right, this is the pattern a plus b times a minus b just equals a squared minus b squared, right? But this time we've got i's in that second term. So it's going to look like a squared minus bi squared, right?
Yeah.
Well, what is bi squared? That's b squared times I squared. But what's I squared?
1.
Negative 1,
Negative 1.
right? Negative 1. So that just becomes
Negative
a squared plus b squared.
Oh, it does.
So every time you multiply a complex conjugate pair out, you're always gonna get a squared plus b squared, right? So if we go back then to this product, what's that gonna give us?
X squared plus 16.
There we go,
Oh, so we just made it easy.
right? So now that's no big deal, x squared plus 16 times q of x equals x to the fourth plus 15x squared minus 16. So if I want to solve for q, all I got to do is just divide my original polynomial by x squared plus 16. Now, the downside is I can't use synthetic division. I got to use long division, but that's all right. It's not that big a deal.
Wait, where'd Q of X come from again?
Well, that's, okay, so question is, where did q of x come from? We know that if the degree of the original polynomial is 4, right?
Yeah.
And each of these are linear, so when I multiply them together, I get degree 2.
Yeah.
Then doesn't mean, this has to be degree 2, because if I'm gonna multiply these out, this has to be, q of x is gonna have to end up equaling, ax squared plus bx plus c, right? That make sense? We don't know what a, b, and c are. But q of x has to be in that form. Right? When I multiply these out, if I distributed the x squared, I'm going to get an x to the fourth, which is going to be my biggest power of x. It has to be, though, right? Because I've got an x to the fourth here.
Yeah.
Everybody see that? Okay? So then q of x is just going to equal x to the fourth plus 15x squared minus 16 divided by x squared plus 16. Okay, so we've done a lot of stuff, taken a lot of detours to get here, but before we go any further, let's just look at what we've done. Let's kind of put this all in perspective, because this really isn't that long a problem when you're doing these problems. I was given one complex 0, right? So I know if I'm given 1, I'm given its complex conjugate also, right? So I now know 2 of the complex zeros, their product, if I take the product of complex conjugate zeros, or factors, I'm always going to get a really easy factor, right? A really simple quadratic factor. And so all I then got to do is divide my original polynomial by the quadratic factor I build from that complex conjugate pair of zeros to figure out what's left over to deal with, right? So we just got to do that math. So this is a long division problem, so you walk me through this. What goes out front?
X squared plus 16.
Okay, what goes inside?
Oh.
Plus 0.
Oh, plus 0.
I got to hold the column for every power of x.
0x.
You write it down, you could
Okay. And,
I have one sloppy little line. Oh, don't do it. Don't do it.
oh, I'm doing it.
Oh.
No.
Okay, so what's that give me then?
Well, you gotta do it.
So x squared goes into x to the fourth how many times?
Twice.
So I'll distribute an x squared, and I'm going to get x to the fourth plus 16 x squared, and I'm just going to subtract the whole thing. So those cancel, I get a 0. 15 minus 16 is negative x squared plus 0x minus 16. So negative x squared divided by x squared is distribute a negative 1, and I get negative x squared minus 16, and what do you know?
Where did the 16 plus 16x squared?
From the outside.
Because, so to get here, all I did was I distributed the x squared, and that gave me that row. Okay?
So then you would distribute the negative 1 into x squared.
Right, I just subtract each one, so I distribute the negative and add, or I can just always remember I'm doing top term minus term below it, okay? And so what's my result then? In the remainder box, I get, yeah, everything cancels, right? I knew it had to be though, that's because we knew that was a factor, right? So we knew that if it wasn't a 0, I would have had to go back and check my work. I would have known I had done something wrong. So I end up then with q of x is just x squared minus 1, right? So going back to the previous page, we know that I could take this line right here, and I'm just going to replace that q of x with an x squared minus 1. And I'm just going to wear this thing out today.
It's his glasses. But wait, there's more. And you didn't get the X.
Okay, so we end up then with,
Oh, so now you multiply. Oh,
Journals are due.
right, if I'm trying to find zeros, this is the only one I need, so what are my 2 zeros I get from that? If I set that equal to 0,
negative 1 on 4. Actually, negative X squared minus 1.
right, plus or minus 1. So now I'll go back to my answers, whoops, go back to my answers, and I get the answers 1, minus 1, and those are all my answers. Okay? How much time we got? 2 minutes. 2 minutes? Okay, so we're not going to do this problem, but I want to see if you can tell me the trick on this guy. Okay, something else that we mentioned but we haven't really used yet.
I've already given us 2.
So this is synthetic division going to help you here? No, not really, right? Because that's going to be a really inconvenient number to run through synthetically. Okay, I mean, I guess it would work, but it would be so hard it wouldn't be worth doing. Okay, but we have another relationship here we can use.
Irrational root theorem.
Okay, yeah, so something else we know. Now let's focus here. We got 1 minute, and then we're going to end this, but I want you to take this thought with you. So if a polynomial has rational coefficients, right, and we know that a plus b radical c is a root of the equation, right, then we also know that that also has to come with a conjugate relationship to another root, and that's going to be a minus b radical c. So in this case, if I write this, the square root of 11 in that form, it's just 0, right? That would be
Plus 1.
0 plus 1 times the square root of 11 must go with 0 minus 1 times the square root of 11,
Which is a negative.
which means I know exactly. I know that f of negative radical 11 must equal 0. So I get 2 of them. I could do the same trick, couldn't I? Right?
Yes, you could.
Plus or minus square root.
Yeah, that would be coming. Okay?
Yeah.
All right. We'll pick it up tomorrow.
That's not-
Work day Thursday.
I got